Hi, my name is Tijana, and today I'll be talking about individual privacy accounting via Rényi filter, and this is joint work with Vitaly Feldman. So this talk is about privacy loss composition, and this is one of the most fundamental problems in the theory of privacy-preserving data analysis. At a high level, privacy loss composition analyzes how privacy of an individual degrades as the number of analyses using their data grows. So this is the usual setup. We have some data set of individuals, and we want to run some analysis on this data set. We get an output from this analysis. Then we feed this output into the choice of the next analysis to run. We get another output. Then we feed the first two outputs into the choice of the third analysis to run, and so on. And so the goal in this setup is to bound the privacy loss of the composed algorithm in terms of the privacy losses due to individual algorithms. And privacy loss composition is helpful because on one hand, it simplifies privacy-preserving algorithm design. So usually we can break down a complex algorithm into simpler algorithmic subroutines. And then we can ensure privacy of the overall algorithm in terms of the privacy of these simpler subroutines. And also this allows individuals to participate in multiple disjoint statistical analyses, all the while knowing that their privacy is preserved. And specifically, we will be focusing on differential privacy. And there are really many composition theorems in the literature on differential privacy. And while they differ in certain aspects, they generally also share one limitation. And that is the fact that all of them summarize each algorithm in the composed sequence using a single privacy parameter. So a typical composition theorem in the literature could look something like this. If AT is epsilon t differentially private for all t, then the composition of A1 through AK will have a differential privacy parameter that's the sum of these epsilon t's. So in the context of the diagram that we had previously, we would associate each of these algorithms in the sequence with a parameter epsilon t. And then we would say that the overall composed algorithm has a differential privacy parameter that's just the sum of these individual parameters. But note that this implicitly ignores any kind of difference between different individuals in the analyzed data set. And specifically what I mean by that is that this parameter epsilon t bounds the worst case effect implied by the removal of the most extreme point. So we are bounding the privacy loss divergence for any hypothetical worst case data set and for any hypothetical individual that we could remove from this data set. But our starting observation is that this ensures that the worst case individual loses at most epsilon t privacy, but a typical individual might actually lose a lot less, because certainly different individuals have different effects on the outcomes of statistical analyses. Say that we have a database of salaries and we want to report the average salary in this data set. Then if we remove an individual whose salary is very close to the average, that has virtually no effect on the final report. Similarly, if we're running a gradient descent and we look at the list of all gradients corresponding to the data points in our data set, then if we remove a data point whose gradient is very close to zero at that given step, then that will have very little effect on the final gradient update. So at some intuitive level, we feel that individual whose removal has very little effect on the final output don't actually lose a lot of privacy by participating at that given step. And we formalize this in this work through individual privacy accounting. And this is essentially a more fine-grained approach to privacy accounting, and it relies on evaluating the effect of a specific data point xi that's in the analyzed data set on the analysis that we're running AT. So in particular, when we run an analysis, we keep track of a different privacy parameter for each individual in the analyzed data set. And we do so for each analysis that we run. And so in short, we provide a tighter analysis of privacy composition by tracking personalized individual privacy losses. And I thank you for your attention.